Lesson: Neural Networks in Cybersecurity. Neural networks have become a cornerstone of modern cybersecurity, offering robust and adaptive solutions to an ever-growing array of cyber threats. These sophisticated systems can learn and adapt over time, providing a dynamic defense mechanism capable of identifying and mitigating risks that traditional methods may overlook. Neural networks, particularly deep learning models, leverage vast amounts of data to detect patterns and anomalies that signify potential security breaches. This lesson delves into the theoretical foundations and practical applications of neural networks in cybersecurity, exploring how these advanced models enhance cyber defense mechanisms. Neural networks, inspired by the human brain's structure and functioning, consist of layers of interconnected nodes or neurons. These networks are trained using large data sets, enabling them to learn complex patterns and relationships within the data. In the context of cybersecurity, neural networks can be trained to recognize the signatures of various cyber threats, such as malware, phishing attacks, and network intrusions. By continuously analyzing network traffic, user behavior, and other relevant data, neural networks can detect deviations from normal patterns, flagging potential security incidents for further investigation. One of the primary advantages of neural networks in cybersecurity is their ability to handle and analyze large volumes of data with high accuracy. Traditional rule-based systems often struggle with the sheer scale and complexity of modern cyber threats. In contrast, neural networks can process and analyze vast amounts of data in real time, identifying subtle patterns that might indicate a security breach. This capability is particularly crucial in today's digital landscape, where cyber threats are becoming increasingly sophisticated and difficult to detect using conventional methods. For instance, deep learning models have been successfully applied to malware detection, significantly improving the accuracy and efficiency of identifying malicious software. Traditional signature-based approaches rely on known malware signatures to detect threats, making them ineffective against new or unknown malware variants. Deep learning models, however, can learn the underlying features and behaviors of malware, enabling them to detect previously unseen threats. A study by Sachs and Berlin demonstrated that a deep neural network trained on a large dataset of known malware samples outperformed traditional signature-based methods, achieving higher detection rates and lower false positive rates. Another critical application of neural networks in cybersecurity is the detection of phishing attacks. Phishing is a prevalent and evolving threat where attackers deceive users into divulging sensitive information by masquerading as legitimate entities. Neural networks can be trained to analyze the content and structure of emails and websites, identifying characteristics commonly associated with phishing attempts. A study by Bonson et al. Highlighted the effectiveness of recurrent neural networks in detecting phishing emails, achieving a detection rate of over 90% while maintaining a low false positive rate. This high level of accuracy is essential in preventing users from falling victim to phishing scams, which can lead to significant financial and reputational damage. Network intrusion detection is another area where neural networks have proven highly effective. Intrusion detection systems monitor network traffic for signs of malicious activity, alerting administrators to potential threats. Traditional IDS often rely on predefined rules and signatures, which can be bypassed by sophisticated attackers. Neural networks, on the other hand, can learn to recognize the normal behavior of network traffic and identify anomalies that may indicate an intrusion. A study by Vinayakumar et al. Demonstrated the effectiveness of deep learning-based IDS, achieving high detection rates and low false positive rates when tested on a benchmark dataset. The ability of neural networks to adapt to new and evolving threats makes them a valuable tool in enhancing network security. The adaptability of neural networks is one of their most significant strengths in cybersecurity. As cyber threats continue to evolve, traditional static defense mechanisms struggle to keep pace. Neural networks, however, can be continuously trained and updated with new data, allowing them to adapt to emerging threats. This dynamic nature ensures that neural networks remain effective in detecting and mitigating new types of cyber attacks. For example, By training a neural network on data from recent ransomware attacks, it can learn to recognize the characteristics and behaviors associated with such threats, enabling it to detect and respond to new ransomware variants more effectively. Despite their many advantages, the implementation of neural networks in cybersecurity is not without challenges. One of the primary concerns is the potential for adversarial attacks, where attackers deliberately manipulate input data to deceive the neural network. These adversarial examples can cause the network to misclassify malicious activity as benign, allowing attackers to bypass security measures. Research by Goodfellow, Schlenz, and Segedi has shown that neural networks can be vulnerable to such attacks, highlighting the need for robust defenses against adversarial manipulation. Techniques such as adversarial training, where the network is trained on both legitimate and adversarial examples, can help mitigate this risk. Another challenge is the interpretability of neural networks. Deep learning models, particularly those with many layers and parameters, are often considered black boxes due to their complex and opaque decision-making processes. This lack of transparency can be problematic in cybersecurity, where understanding the reasoning behind a detection is crucial for effective incident response. Efforts to improve the interpretability of neural networks, such as the development of explainable AI techniques, are essential in addressing this issue. By providing insights into the decision-making processes of neural networks, XAI can enhance the trust and reliability of these systems in cybersecurity applications. Moreover, the effectiveness of neural networks in cybersecurity depends on the quality and diversity of the training data. A neural network trained on a limited or biased dataset may fail to generalize to real-world scenarios, leading to poor performance and increased false positives. Ensuring access to high-quality representative datasets is crucial for the successful deployment of neural networks in cybersecurity. Collaboration between industry, academia, and government agencies can play a vital role in facilitating the sharing of relevant data and knowledge, fostering the development of more robust and effective neural network-based security solutions. In conclusion, neural networks offer significant potential for enhancing cybersecurity through their ability to analyze large volumes of data, detect subtle patterns, and adapt to new threats. Their applications in malware detection, phishing prevention, and network intrusion detection demonstrate their versatility and effectiveness in addressing a wide range of cyber threats. However, challenges such as adversarial attacks, interpretability, and data quality must be addressed to fully realize the benefits of neural networks in cybersecurity. Ongoing research and collaboration are essential in overcoming these obstacles and advancing the state-of-the-art in neural network-based cyber defense. As the digital landscape continues to evolve, neural networks will undoubtedly play a crucial role in safeguarding our systems and data against increasingly sophisticated cyber threats.